In this exercise, we're going to find the volume of the solid between the paraboloid, z equals x squared plus y squared, and the sphere, x squared plus y squared plus z squared equals 2. I will tell you, when we see the volume of the solid between the paraboloid and the sphere, when you draw it, there could be some ambiguity. So I'm going to tell you that we're talking about the inside portion of the paraboloid. What I'd like for you to do is sketch the sphere and the paraboloid in R3, and then see if you can set up the integral and then come back when you have gotten that far. All right, let's see what we've got here. Here's the region in R3. We have the sphere of radius square root of 2, inside of which is part of a paraboloid. And we have here the curve of intersection between the paraboloid and the sphere. We're going to need that because we need to know what the region D is, the projection in the xy plane. For that, what I'm going to do is take z equals x squared plus y squared. I'm going to replace x squared plus y squared in the equation for the sphere. And by doing that, we get that z plus z squared is equal to 2. And z is then equal to negative 2 or 1. Z equals negative 2 doesn't have a physical meaning in this situation, so we're going to dump that part, and we know that z is equal to 1. If z is equal to 1, that gives us a circle of radius 1 in the xy plane for our projection. Therefore, we know that r will go from 0 to 1, and theta will go from 0 to 2 pi. As far as the limits on z, z has a lower limit related to the paraboloid and an upper limit related to the sphere. So z goes between x squared plus y squared and the square root of 2 minus x squared minus y squared. In cylindrical coordinates, that means that z goes from r squared to the square root of 2 minus r squared. We then have our volume integral. It's the integral from 0 to 2 pi of the integral from 0 to 1 of the integral from r squared to the square root of 2 minus r squared. Our integrand is just dv. And in cylindrical coordinates, that's r times dz dr d theta. Now that we're solid, that we have the correct integral, I'd like for you to go ahead and compute it and then come back again when you're done. For the integration portion, there's no theta in our integral. So from 0 to 2 pi d theta, that's just going to give me 2 pi. And then integrating with respect to z and evaluating at the limits of integration, we end up with v equals 2 pi times the integral from 0 to 1 of r times the square root of 2 minus r squared, that's from the upper limit for z, minus r cubed, that's from the lower limit of z, also with the factor of r, times dr. Integrating with respect to r, we need to multiply and divide by negative 2 for r times the square root of 2 minus r squared, so that we can use the power rule. And then, of course, r cubed is going to use the straight power rule. So v is equal to 2 pi times negative 1/2 times 2/3 times the quantity of 2 minus r squared to the 3/2 power minus 1/4 r to the 4th, evaluated from 0 to 1. At the end of the day, when this is simplified, we have that the volume V is equal to 4 pi times the square root of 2 over 3 minus 7 pi over 6. Very common answer. You see that all the time, don't you? I mean, like, pick a number between 1 and 10. 4 pi times the square root of 2 over 3 minus 7 pi over 6. Maybe not. Anyway, common or not, that's our volume.